Okay, this section's incredibly important to calculus, okay? And here's where we're measuring the instantaneous rates of change on any graph. And in this case, the graphs are going to be rational. So let me just enlarge this and show you what they're doing. This is incredibly important if you're going to proceed through the maths and sciences. All right. So they want to use on either side of the value of 5. First of all, let's use Desmos, because when you reverse analyze something, it's much, much easier. So we're going to pull up Desmos. We're going to put on the graph f of x is equal to 5x divided by 2 plus x. And this is what it looks like. So we'll bring it over. And I'll just make this graph bigger. Yeah. Whoops. There we go. Just select it. So this is the graph they want to analyze, and they want to analyze around when x is 1.5, right there. This is the graph they want to analyze. But I want to show you what it looks like. This is what the graph looks like. And it's a typical reciprocal, where, as you would expect from the bottom, the asymptote is going to be at x is equal to minus 2. And also from 5x, you will expect it to go through the point 0, 0. And it does. There are just a couple things to note about this graph. But they're very interested at this point. When x is 1.5, y is this. And we're going to graph that point. 1.5 comma f of x, or f of 1.5 right there. We're going to label it. So they're very interested in this point right here. And I'm going to unlabel the 0.0 because that was just for demonstration purposes. They're very interested in the rate of change right there. What is the rate of change? Well, the rate of change is actually a measurement of the slope at any point. The slope at any point. And let me just show you an interesting thing we can do with the slope. I'm going to bring up a whole different thing here. And you'll notice that each square is 1 on here. A slope at this point is simply a tangent line. We're going to make a blue line, and we're going to try to make it look a tangent line. A tangent line runs, and that's not quite it. It's going to be about there. A tangent line touches the slope once, as opposed to a secant line. A secant line, that's a secant line right there because it goes through the graph twice, or at least twice. That's a tangent line. It's going to touch the specific point of interest once. And the other thing interesting about a tangent line is it forms a 90-degree angle from a line that shoots straight out from that point. So that is roughly tangent line. And all we're going to be doing is measuring the slope. But let me show you. Sometimes they're going to give you a graph. And you can measure the slope of any graph. Let's have a look at this. We can see the triangle here goes, if we count the squares, the triangle here is going 5 across, and it's going 4 up for the particular triangle I drew from that blue line. Yeah, using the blue line. This is the triangle I'm measuring. And triangles, doesn't matter where I measure it, as long as the blue line forms the hypotenuse of it, and it forms a 90-degree angle right here, right? 90-degree angle right there. That is going to give us the slope. We can see it's roughly 504. That's 5 over 4. How do you do slope? Well, slope is always y is equal to rise divided by run. And rise is always the furthest right y minus the furthest left y. That's rise. And run is always the furthest right x minus the furthest left x. And we can see from the y2, the point I've taken for y2 is right here. It's right there. And we can see the point for y1 is right there. We can see that point up here is 5, 5. And we can see that point down here is 1, 4. No, hang on, 1, 1. No, 0, 1. Like that. So now we have our x1 and our x2, or sorry, our x1 here and our y1. And we have our x2 here, 5, 5, and our y2. Well, it's clear our y2 is 5. And we're going to get into faster ways of doing this. Our y1 is 1, our x2 is 5, and our x1 is 0. If I do the rise over run, rise, which is y2 minus y1, my rise is 4. If I do a run, it's x2 minus x1, and my x1 is equal to 0. The run is 5, which means my rise over run is 4 over 5, which is roughly 0.8. So my result I can expect around 0.8. Now this is always going to be inaccurate because it's visual, and I just wanted you to show you that you can determine a tangent line from graphing and using the old technique of rise over run of a right angle triangle. And the reason I do this is so that students understand that instantaneous rate of change is the exact same thing as finding rise over run for a point using these methods. It's just we're going to use algebra instead of graphing. So that means we can use this. They want to see what the rate is between just to the right of this and just to the left of it. So the easiest point just to the, that's a graph, the easiest point just to the right of it is to take a point that's just 1.50001. That's just to the right of it. That's an x value that's just to the right of 1.5. Well, to find the point just to the right of that, we need to take f of 1.50001, like that. Now, if I unlabel this one just for clarity's sake and label this one, we can see that, do I have the right number of zeros? There's 5 zeros. Yep. We can see that point to the right is just 2.143 instead of, oh, it looks very similar, doesn't it? But don't worry, we're going to let calculus, or we're going to let the computer do it for us. Now, if I take a point just to the left of 1.5, that would be this point, 5 nines. And it would be this y value. And I can just let Desmos do it for me. Now, interestingly, this point's going to be very similar in the y value. That's simply because Desmos is rounding it up. But when we do calculator, it will be quite much simpler. So all we've discovered here is that x1 is equal to 1.499999 because it's to the left, and that x2 is equal to 1.50001 to the right. And we've also learned that y2 is the point f of x2, 1.50001. We might as well let the computer do it. And y1 is the point just to the left, 1.499999. Well, now we can just say rise is equal to y2 minus y1, and it will be able to do it for us. Now, just a moment, let me just get rid of rise, and we'll just say y2 minus y1, and it gives it to me. And then we can determine that run is x2 minus x1. Now, guess what? Since we added 0.000001 to the right, and actually I did not enough nines on the left, we're going to see essentially, yeah, so I did too many nines, so I might as well do this. There we go. Did I get it right? No. It should just be 0.001. So I got, how many decimals here? I got 1, 2, 3, 7, and here I have not enough. I only got 6, so I got to add an extra one. Let's see if I get, close enough. It doesn't matter. Oh, no, that makes sense. No, it doesn't really. 7 decimals. I got to add another 9 here. Did I get it? Yeah, there we go. 0.00002. So there we go. I got the right number, 9. So I got to have 6 nines. All right, so now we have 2. Now we can just take these and just have it do rise over run. And remember, we're supposed to expect about 0.8. 0.8. And there we go. We got 0.8163, just like our graphing told us. And that's the rise over run if we take a point that's just to the right of our point of interest and a point that's just to the left of our point of interest. And that will give us rise over run. And that's precisely what the textbook does. The textbook notice what the textbook does, though. It takes a point that's quite widely to the right and widely to the left. And the more wide to the right and wide to the left you go, the less accurate your instantaneous rate of change. Notice that the broad one gives 0.817, then it goes 8.16, 0.816. And you might think those are all the same, but that's just because they haven't done the decimals deeply enough. We can see that ours is 0.816326. It's very accurate. And the smaller you make this number, the more accurate it'll get. Like if we add more zeros to it and more nines to it, the more accurate our number will be. Now, what this is teaching us in calculus, what we learn is a formula of how to derive a formula instead of doing this over and over again to determine this rise over run. Another key point that if I look carefully at x2 minus x1, it is always going to be the point that since I added 0.00000000001 to the right and then took that off to the left, it's obviously going to be the total of those two. It's going to be that. And so you're going to reach a point where you don't even have to do x2 minus x1. All you have to do is put in the amount that you were adding or subtracting from it. That's going to be called h later on. And you'll get the correct answer as well. So you end up never even having to do x2 and x1 because you know you're adding 0.0001 to the right side and subtracting 0.0001 from the left side, and you know that that will always add up to 0.002. And you're going to reach a point where you're going to even use 0.001. Like we're never going to even bother with the 5. We're just going to be bothering with, we're going to use 1, and we're just going to make it 0.5 instead. And we're going to make the x, yeah, that's what we're going to do instead. And you're still going to get the accurate answer. So you're going to make a space that's very small between your point of interest and a point that's just to the left. This is taking to the left of interval. The one we just did was to the right and to the left, called a central interval, which is what they're getting at here. And then they show you that graphing, see, graphing, we could have done it graphing as well. And then they teach you the h, see? So there's the h where instead of coming up with x2 and x1, we just figure out how much interval we're adding to the right or to the left. And then they teach you this is to the right. This one's to the right because it's 1.5 plus a small interval minus the original point. And then you end up coming out with a solution. They give you a couple more questions, and they want you to get used to this formula, f of a plus h minus f of a over h. And you might say, Peter, why did you spend time doing it over here like this? Well, let me show you. They were interested in this point, right? 1.5. So I'm going to put it on the map. I'm going to label it. They're interested in the average rate of change of that point. Well, what they're saying is you're going to add a little small amount to your x. That's my small amount. That's essentially x2 minus x1. I don't have to do x2 minus x1. That's the small amount I'm going to change. And then they're going to ask me to take the f.15, and they're going to ask me to add that small amount, h. Now, I could put the 0.00001 in here and get the same answer, but I've already labeled h as equal to it, so I do that. Then they're going to let you use the formula of this, that slope is going to be equal to f of 1.5 plus h minus f of 1.5, and that essentially is y2 minus y1. This is y1, and this is y2 when you add a little amount to it, all divided by h. You don't need the equals. All divided by h. Oh, you got to make sure you do it like that. And there you go. We get the same slope that we got before. Now, interestingly enough, the smaller you make your h here, the more accurate your slope gets. And notice that all I have to do is change my h because my formula right here does the calculation for me depending on what I change my h to. So this Desmos is a very handy tool to start learning with. Just don't use it to cheat because when an exam comes, you're not going to have Desmos handy. All right, let's try to do some questions now. This is a very important concept because all of calculus is this. This is all the calculus. It's all about learning how to do rates of change for every function graph you've learned. Now, some of these I'm going to answer using Desmos because I don't want to spend all my time doing calculator. But you will be expected to do it by calculator and sometimes by graph as we just did. So we're going to focus on these questions right here. Good. Okay, so we're going to continue this. This now asks for about average rate of change between x is 2 and x is 7. Now I needed this graph, and they wanted me to use graphing technology, so that's a perfect example. So if we look carefully between x is 2 and x is 7, we're talking, so 8, so this is 7 in the middle here, so let's use a black line. We're talking between this point, and let's make it a little thinner. We're talking between that point. somewhere there, and this point. So what we do is we find out where it crosses the line, and we draw a nice green line across it. So it crosses the blue line here, down to here. Now if we're having trouble seeing the tangent, what we can do, or the average rate of change, what we can do is just zoom in on it. And we can draw as big a line as we want to represent that line, so long as we're right on top of it, close enough, right about there. And then we can use the lines outside of that more accurately. And remember that each square here is 2 going up and 2 going across. So there's a nice spot to use, right about there. See, and the nice thing is it doesn't matter how wide you make this triangle, you can make it as wide as you want. So then if I count the squares here, I go 1, 2, 3, 4, 5, 6, 7, 8. And 8 times 2 is 16. That means the run is 16. If I go down, I got 1, 2, 3, and it's going to there. No, I can use my whole triangle. 1, 2, 3, 4, which is 8. Which means the run is 16, the rise is 8. 8 over 16 is a half. So that means the average rate of change is a half, which means it's going to go down 1y it's going to go down 1y and over 2 x's. That's what 1 over 2 means. It's going to be going, since it's negative, it's negative a half. It's going down. So it's going to go down 1y and over 2 x's. 1y and over 2 x's. This is fairly obvious here, where it kind of goes down half a y. It goes across 2 x's. Then it goes down half a y again and goes across 2 x's. Then it goes down half a y there and goes across 2 x's. So it's quite clear this is probably accurate. So the average rate of change here is negative 1 over 2. And it's negative because a line that goes down like that is a negative slope. Copy the graph and draw a tangent line at the point x is equal to 2. Okay, so let's remove all our work. And we can see x is equal to 2. The tangent line is going to be very different. Just going to zoom in. X is equal to 2 is right there. I'm going to get rid of those lines. If I look at this point right here and try to draw a tangent line, it's like that. So just ignore that in the background. It's like that. And you'd put it like this. But the same thing goes. We can make this tangent line as long as we want, and that's still not an accurate 90 degree right there. I'd say it's more like that. And this tangent line is right angles to the spot that we're looking at, and then we should just try nice even spots. I would say it's rough, but I would say this one, red or yellow is good, down to this one. That's nice even numbers. So I can see that this rise is much bigger. It's 1, 2, 3, 4, 5, 6. And each one is 2. So it's going down negative 12. And the run is always positive, is 1, 2. So it's going over 4. Negative 12 over 4 is negative 3. So that means it's going, and really it's negative 3 over 1. And what that means is it's going down 3 units and across 1, down 3 units and across 1. If this was an accurately drawn tangent, I think actually the tangent might be even sharper than that. That's where graphing is always going to produce a little bit more inaccuracy than anything else. Oh boy, this is a tough one. I would really not bother with that. Instead, I would take this graph here and use the x plus 2, x minus 1, and use that in Desmos. So to answer this question, they're trying to find an instantaneous rate of change between x and 2.1. So for that, I'm going to use my Desmos. I know you'd like me to do it by hand, and I'll sort of do it by hand. First thing I'm going to do is make f of x equal the graph, x plus 2 divided by x minus 1. And try to use your parentheses because it's going to be a lot easier. Now this is going to see how accurate my last answer of minus 3 over 1 was. And I don't think it was. I think we're really dealing with like minus 4. And I'm going to find my f of 2. So really we're talking about the 2, comma 4. That's the point we're talking about. And then I'm going to find a point that's just to the right of that, 2.1. And to find that, I'm going to have to do f.2001, which turns out to be a point like this. Now, it looks like it's 4, but in reality, if I just do this, it's really 3.9997. So we're going to use it like that, which means if I'm going to label this, my x1 is 2, my x2 is 2.001, and it's quite obvious that if I take x2 and subtract x1, I'm dealing with an h, which is the difference between the two, of this. However many zeros I threw up there, that's my h. And if I look at my result of f2.0001, and then I subtract my f2, I'm going to get a very small number. So what I'm going to do instead is I'm going to ask it to calculate f of 2 plus my h, which is the same number we got, minus my f of 2, and all of it is going to be divided by my h. And look, I was pretty close. It looks like -3 was the actual instantaneous slope. And keep in mind, the more we make h smaller, the more accurate our slope will be. And so, yeah, it jumps past 3, you'll see, a couple times and gets confused. But overall, we can see that the actual answer is probably -3, which means that tangent I drew was damn accurate. Good for me. This is just, I know I'm using the calculator to do it, but this is f of y2. It's f of 2.001, the point just to the right of 2. The 2.001 is x2. x2 minus my original x1 will always give me my h, so you're going to just start learning just to use h instead of doing x2 minus x1. This is my y1 here, and this is my y2 here. And if I skip this instead, I can just put the y2 in. So here's the y2, 3.9999997 minus 4. I'm going to get the same answer. So I got to make sure I get the right number. Oh yeah, was it 4? I got to make sure I get the right answer. So I got to make sure my h has as many. Yeah, so the problem is you can't have more zeros in the h than you add to the to the f2. See, this one had 1 less 0 than my h did, and I cannot use that unless it matches my h. Otherwise, you get -30 instead of -3. So this now matches, and this is sort of, that's y2 minus y1 over x2 minus x1, except x2 over minus x1 is always the h, because we artificially added h to create x2, so why bother if we're just going to add it and then subtract it? We might as well just use h down there. But look at that. Damn accurate. All right, next question. Using graphing technology to estimate the instantaneous range. So yeah, so I didn't bother with this because it meant graphing-wise I'd have to draw a ridiculously tight line, and it's the same thing as I did up here, so we can see that I just answered 3. So there you go. Okay, so number 4. Let's go on to number 4. Estimate the instantaneous rate of change. So estimate usually means don't do any calculations. But we're going to figure out what 2 is. So we know that when we put 2 in here, it's -1. So if we're going to take a number that's just to the right of 2, let's take 2.001. And let's just pretend x is 2.001. And clearly 2.00, we'll use 5 zeros. 1 is to the right of 2. So it's going to be 2.001 minus 4. Now, if this ends up being -1.9999999. And just to make sure, we'll put it in the calculator. What is 2.5 zeros minus 4? And sure enough, it's 6 nines. And that's what I have. So now we're going to take that and divide it by -1.999. So 2.01. Now what's interesting is I can take that and divide it by 2.00001 and then just flip it. And when I flip it with 1 over x, this is what I get. -1.0001. Oh, actually, I can't do that. So that is, yeah, that is going to be my y. So that means when x2 is 2.001, my y is this. And I'll just use this. So now if you're going to take an FA plus h, that's the same as the y I just got. And then if I have to subtract the 1 above, minus 1 minus minus 1 is plus 1. Negative 1, negative 1.0001 plus 1 is just the decimal. And then it's got to be divided by my h. My h is 2.001 minus the 2, which is this. Now the problem right now is it looks like it's 1, which would mean it's pretty much going diagonally right, because I've got 5 zeros here and 5 zeros here. So that means my rate of change is estimated at about 1. To confirm this, we're going to take Desmos. We're going to put in the formula x divided by x minus 4. We're going to find the point f2 to confirm that we have the right one. We're going to use that h. So f2 is indeed negative 1. So that means we're going to take f of 2 plus h minus f2, and we're going to divide that all by h. And sure enough, I get negative 1. So yeah, I forgot that this is a negative 1 over here. So we get this as the result. Pretty much negative 1, which is what we had. Well, I had 1, but I'd forgotten that this is negative. So we see that negative 1, we're pretty much bang on. Select a strategy to estimate instantaneous rate of change. So in this case, I'm just going to take a point to the right of 13, to the right of 5, to the right of 4, and to the right of minus 3. But you can also take a point that's to the right and to the left, or you can take a point to the left. So there's a couple strategies. And technically, a graphing calculator is still a strategy. So you could always just say, I'm going to do it by graphing calculator. Now, I would sit here and do the calculations all night long if I want. But instead, I'm just going to rely on Desmos to show you the technique. So if you're talking about the first formula, we've got 25 minus x. And they're saying when x is 13. So we're just going to call that x1 is 13. x2 is just going to be a number plus that 13, like this. We're just going to use a simple one, 3 zeros. Okay? So that's just to the right of 13. F of x1 is going to be what we call y2, or y1 rather. So if I can just figure out what it is, this, I can just make that my y2, or my y1 rather. And my y2 is going to be f of x of 2. So this is going to be my y2. Now notice that this, when I subtract this, is my h. So it's just going to be this decimal here. So I could just write my h is that decimal here. And I can just skip x2 and x1. Now, let's see what happens when I do y2 minus y1, all divided by h. So that should be the answer I get. But now let's do it the way they have it in the book. We're talking about an x of 13 here. So technically, f of 13 plus my h minus f of 13 divided by my h should give the same answer. So I'm going to do that, and then I'm just going to backtrack to what I had. There we go, that's what I had. And let's see if I get the same thing. I do indeed get the same thing. So you can see that you can do it this method mathematically, or you can just jump right to this technique, which is f of 13 plus your h minus f of 13. Notice that if you choose a point to the right of your 13, this has to be on the left. It always has to be this minus that divided by h. In other words, the original point has to be on the right side of the equation, and this is the y2 on the left. That's because if we choose a point that's just to the right of 13 by adding h, we must put these y2 and y1 in the correct order. We're going to continue with each of these formulas. 17x plus 3 divided by x squared plus 6. I'm going to use the same h, but this time we're going to just use this formula. And this time they're looking at x right here. We're looking at x is minus 5. So we're going to do f of minus 5 plus h. And don't forget to put f of minus 5 here. And we're going to get the answer. Now, if we were to calculate f of minus 4.9999, that would be the same as our y2. That's a point to the right of y2, to the right of my x. And my y1 would be the same as f of minus 5, which is this here. That's my y1. Which means my y2 minus my y1 divided by my h should give the same answer. And it does. Pretty much. The error here comes from rounding. So down here it's rounding, and up here it's not. The error also comes because I'm rounding here. And whereas here, the calculator is using the full decimals. That's the benefit of this formula. We're going to continue on and use the same formulas. We're talking about x plus 3 divided by x minus 2. And we're going to do, this time, it's for 4. And we get that. You can go the long way and you'll get the same answer, but essentially it's 4 plus my h, and then this is my y2 when I plug it into the function. And this is my y1, just f of 4, and then you're just dividing by h. And then finally, even though this is a complicated formula, this last one, it will work no matter what formula you use. Well, let's do the last one by hand and show you how it's done. So the first step is we need to find the y that matches this. So we got to put minus 3 in there. Minus 3 squared is 9, times minus 3 is minus 27, plus 5 times minus 3, which becomes minus 13. So we're just doing minus 13, plus 6. So this minus 27 minus 13 is minus 40, and plus 6 becomes minus 36. Sorry, minus 34. And then downstairs, minus 3 plus 6 becomes 3. So we have to take minus 34 divided by 3, and we're going to get a decimal that's probably got a bunch of 0.333333 in it. That negative, and we're going to divide it by 3. Yeah, negative 11.333. So that means we're talking about this point. Whoopsies. That point. To find the corresponding point, we've got to take a point just to the right, which is negative. You'd think it's negative 3.00001, but it's that one actually. And if I use that one, my h is 0.0001, 3 zeros. Now I've got to find the corresponding y to this. Now this is a much harder calculation because I now got to take minus 2.999 and put it in where I see x over and over again. So what I'm going to do is take 2.9999 and make it negative. And I'm going to put it in my memory. So first thing I'm going to do is I'm going to square it, and I'm going to multiply it by 3 negative equals. And then I'm going to add it to 5 times it. Great. And then I'm going to add 6. I'm going to hit equals, and I'm going to divide it by x, open brackets, my new x, plus 6, close brackets. And I'm going to get that. Now keep in mind this number should be very close to the number you got up above. And if it's not, you made a calculation error. This is my y2. So this minus that. So I'm just going to leave it in my calculator. That minus minus becomes plus. And my h, remember, is 0.001. 0.001. You got to get this right, otherwise you. So I don't know if it's. I don't think I got it right. So I'm going to try this again. So I got to take 11.99988333822, make it negative, and I've got to subtract my y1, and minus 11.3 becomes this. And it should be a very tiny number. It's not really. And then I've got to divide it by my h. Okay, well, it popped up the same thing. It's saying that this is the slope and it's going downwards. So it's saying this is my rate of change. Let's use Desmos to see if we got it right. So we're going to do, open brackets, minus 3x squared plus 5x plus 6 divided by x plus 6. And we're going to do f of minus 3 plus h and f of minus 3. Ah, you see, I got a serious calculation error somewhere in there. And no doubt it might be my h. So I should make sure that I got that 2.999 is indeed. So it's minus 3 plus 0.0001 negative 249. Yes, it is. So I got that right. So let's just figure out what that one is. We'll just leave that there and we'll go to this one. Let's figure out what f of negative 2.9999 is. Okay, I got that right. Let's see, negative 3. I got that wrong. So I got that wrong somehow. So that should, let's try that again. Negative 3 squared is 9, times minus 3 is minus 27, minus 15 is minus 42. That's where I got it wrong. Plus 6 is indeed minus 36, divided by 3, which is minus 12. Yeah, so that's where I got it wrong. So that means I should have had, which is why right there, this should have been the clue. This number and this number should be very close together, and they're not. That's why this should have been negative 12, which is very close to that number. So now we'll do it calculating, and that's why, graphing calculators are superior sometimes. We're going to try it again, 9988333 822, and we're going to subtract the real number, which ends up being plus 12, and it's going to be divided by my h, 0.0001, and hit equals. And still got it wrong, so hit clear. So we're going to take my f2, which is 11.9988333 negative. We'll do the proper way, minus 12 negative equals a very small number divided by a very small number. Oops. Equals. There we go, 11.666. That's what it's saying. Let's see what Desmos says. Yeah, there we go. We got the same as the calculator, 11.6666. So you can see mathematical errors are a big part of this. It makes it difficult.